Hello and welcome to the pre-lab lecture video for Lab 10, Experiment 6, which is titled The Mole, Counting by Weighing. So the objective of this experiment is for students to become familiar with how atoms are quantified and to be introduced to the concept of the mole. So let's start with the pre-lab. The pre-lab starts by asking you to determine the atomic mass of the following to the nearest hundredth of atomic mass. So remember, nearest hundredth means you should be rounding to the hundredths place, which is 2 decimal places or 2 places after the decimal. Remember that you can find the atomic mass on the periodic table. And because it's asking for atomic mass and not molar mass, the units are atomic mass units, which are abbreviated AMUs. The second question is asking you to calculate the molar mass of the following to the nearest hundredth of molar mass. We're still going to get the values for the mass of each of the individual elements from the periodic table, but because it's molar mass, the units are grams per mole. So just as a reminder, from the periodic table, you can find the mass, and that can be written in atomic mass units for the mass of an individual atom of an element, or in molar mass, right, for the mass of a mole of atoms. And if it's a molecule or a compound, there'll be multiple atoms, and so you would want to just sum all of those up, right? So for example, for copper oxide, if it was copper 2 oxide, right, well, really, then you would need to, the formula would be CuO, right? So you would add up the mass of copper, right, and the mass of oxygen. I included another larger periodic table where you can see the mass of all of the elements, all the way in most cases to the thousandths place. So it gives you plenty of significant figures to be able to do your calculations. Question 3 asks, given 100.0 grams of each of the following items below, calculate the number of moles, round off based on the mass given. So that means basically look at the mass given to determine how many significant figures you should have, right? And since we are going to be multiplying and dividing, we look and see that there are 4 significant figures here. So you should have 4 significant figures in your product. And so we would start by, for example, taking 100.0 grams of phosphorus trifluoride and then multiplying that, or really dividing it by the molar mass. We want to make sure that the grams are in the denominator so that the units of grams will cancel and you'll be left with units of moles. You would do the same thing for B, C, and D. The only difference is you'll be using the molar mass of B, C, and D, which is different because of the different halogens used in the formula. For question 4, calculate the number of molecules given 1.000 grams of the following. Again, 4 significant figures, so we'll make sure our answer is in 4 significant figures. For example, again, we could start, and it looks like I made a mistake here. So instead of 100 grams, it should read 1.00 grams. Dividing by the molar mass gives you the number of moles. And then using Avogadro's number, right, for the number of molecules in a mole will give us the number of molecules right? Given whichever formula we're talking about, in this case, phosphorus trifluoride. So let's move on to the experiment. In the experiment, let's talk about part 1 first, which is establishing the mass of individual elements and molecules. So we're going to be using bolts and hex nuts to represent elements. So for example, you could imagine the bolt might be oxygen and the hex nut might be hydrogen, or representing hydrogens. So that's the idea. They're representing sort of theoretical elements. Element number 1 is going to be the hex nut, and element number 2 will be the bolt. And part A wants us to determine the average mass of a single hex nut and a single bolt. And we're going to do this by weighing the maximum number of each and then dividing by the number that you weighed. For example, if you're provided 12 hex nuts, you would want to weigh all 12 hex nuts together using your digital scale, and then divide by 12 to get the average mass of a single hex nut. Same thing with bolts. Use as many as you can. Divide by the number that you weighed to record the average mass of a single bolt. Remember to record all the digits on your digital scale because all of them are significant. Then we'll move on to part B, where you're going to be determining the average mass of some molecules. And we can think of number 1 as being Bn, because it's composed of 2 elements, which are 1 bolt and 1 hex nut. Bn2 would be composed of 1 bolt and 2 hex nuts, and so on. So you want to make the maximum number that you can, given the number of bolts and hex nuts you were provided in your lab kit. And it will tell you in the table how many you should be able to make, right? Weigh as many as you can together and divide by the number that you weighed in order to get the average mass of those molecules. After that, we'll move on to part C, which uses Lego bricks. For the Lego bricks, you're going to be doing your own measurement and also looking at a video to record measurements from the video. I included the link to the video in the PowerPoint slides, and you can also find it in the lab manual. You were provided 3 Lego bricks, 1 E brick and 2 F bricks. They're named E and F based on the number of pegs on the Lego brick, right? The one that is shown in red here has 8, so it was E for 8, and then we have the one that's shown in blue, which has 4, so F for 4. You should have, again, 1 E brick and 2 F bricks, but the colors may vary in your kit. However, the mass will not vary, so don't worry about the color of your individual Lego bricks. So first, you're going to be measuring the mass of the individual elements E and F. In your lab manual, it says to weigh 2 E bricks and divide by 2, but you were only provided with 1 E brick. So just weigh your 1 brick and don't divide. And remember to record all of the numbers provided by your digital scale. For the F brick, you were provided 2 in the kit, so go ahead and weigh both of them together and then divide by 2 to record the average mass of the F brick. You can also then look at the video where 10 E bricks were measured and 10 F bricks were measured, and record the mass of the average mass of 10 bricks as well in your data sheet. After that, part 3, it wants you to measure the mass of molecule EF2. So you can assemble EF2 by putting together all 3 of your bricks and measuring the mass. And you could also record the video data, which is the average mass of 10 EF2 molecules. The last part in part C is to calculate the percent difference between your measurement and the video measurement. So it tells you exactly which data to use to plug in to the percent difference equation. So look for C3A and C4A. These lines here, right, the vertical lines represent absolute value. So in case you were to get a negative number, just change it to a positive number and then multiply by 100 to get your percent difference. In part 2, we're going to practice counting by weighing. Obviously, it's impossible to count the number of atoms, right, in a sample of something. But we can still weigh a sample of something and then use that weight, right, with conversion factors such as the molar mass and Avogadro's number to determine the number of moles and also the number of molecules or the number of atoms, right, in a given sample. So that's the point of part 2. In order to get the data for part 2, you will need to use the data that is assigned to you from your unknown, and that's going to be given in Canvas and will be different for different students. So be sure to record your unknown number in your data sheet. If you don't record that, we won't be able to note if any of your data is accurate, and so you're going to lose a lot of points. In part 2, we will be determining the number of hex nut elements in a sealed container, the number of BN1 molecules in a sealed container, the number of EF2 molecules in a sealed container, and then also determining the identity of 2 molecules in parts G and H, and the identity will either be BN, BN2, BN3, or BN4. So let's go ahead and look and see what the data tables look like in your lab manual. Again, you're going to be getting this data from Canvas, right, as part of your unknown. So you won't actually have these sealed containers in your lab kit. This is all data that's given to you on Canvas. So part D is going to be determining an unknown number of hex nuts in a sealed container. So in order to do this, you're given the mass of the container and the mass of the container plus some number of hex nuts inside. In order to determine the mass of the hex nuts inside, you have to subtract the mass of the container from the mass of the container and hex nuts. This will give you the net mass of just the hex nuts in the container. And given your knowledge of the average mass of a hex nut found in the experiment in part A, you will be able to determine how many hex nuts are in the container. Again, you have the mass of all of the hex nuts in the container, right? And if you divide that by the average mass of a single hex nut, which you found in part A, that will give you the number of hex nuts in the container. Part E is going to be doing something very similar, but in this case, there wasn't just a number of hex nut elements. Now we're looking at BN1 molecules. So there's some number of BN1 molecules in an unknown container. So we'll need to take the mass of the container by itself and subtract that from the mass of the container containing the unknown number of BN1 molecules to get the net mass of BN1 molecules in the container. Divide that by the average mass of a BN1 molecule, again found earlier in the experiment, to determine the number of BN1 molecules in the container. Part F is very similar, but now we were back to the Lego bricks, right, with molecules EF2. Again, this data is given to you from the unknowns on Canvas. You'll be given the mass of the container, and some number of EF2 molecules that's unknown. Subtracting the mass of the container from the gross mass of the container and the molecules, you'll get the mass of some number of EF2 molecules. That's called the net mass. Divide that by the mass of a single EF2 molecule found earlier in the experiment, and you will determine the number of EF2 LEGO molecules that are in the unknown container. Part 3 is still going to be using unknown data, and it's called identification of an unknown based on average mass. So in this part of the lab, parts G and H, you will be determining the identity of a molecule based on given data from your unknown. So your answers to both parts G and H will be either BN, which might be written in Canvas as BN1, BN2, BN3, or BN4. So again, you're going to get this data from the unknown data provided to you on Canvas. You're going to write down in both parts G and H the number of molecules in the container that's given to you, the mass of the container plus the unknown. Subtract the mass of the container from the mass of the container and the mass of the unknown to get the net mass of the unknown. And then take the average mass of unknown 1, right? And given the number of molecules, you'll be able to figure out the formula of a molecule in the container. So again, your answer will be BN1, BN2, BN3, or BN4 for both parts G and part H. So again, once we have the average mass of the unknown, right, and we know how many molecules are in the container, then we can figure out, right, how many, or what would be the mass of just one of those molecules. And if we match that to earlier data, that should match either BN1, BN2, BN3, or BN4. For part 4, we're going to be measuring the mass of water and sugar. So the part J is titled the number of moles and the number of molecules. So we're just going to be doing the calculations. We're going to be acquiring the data, right? Getting the mass data at this part, and then in the post lab, we'll be doing calculations to convert the mass that you record right now of water and sugar and the iron cube, and converting that to the number of moles and the number of molecules. So for now, again, we're just using our digital scale to take measurements. In part 1, it just wants you to record the mass of an iron cube, which is shown in the photo. Remember to record all of the digits shown on the scale in the photo. And then next, it wants you to measure the mass of 50.0 milliliters of water. For that, you're going to tare your clean and empty 50 milliliter graduated cylinder. Remember, tearing means to place it on the scale and press the tare button so that the scale reads 0 when the graduated cylinder is on the scale. Then you're going to add water to the graduated cylinder carefully, making sure not to spill any water on the outside of the graduated cylinder or on the scale. And then you're going to bring that amount of water precisely to 50.0 milliliters of water. Remember, the bottom of your meniscus should be exactly at the 50.0 mark on your 50 milliliter graduated cylinder. So you can fill it very quickly at first, but as you get close to the 50.0 milliliter mark, use your plastic pipette to add the remaining amount of water dropwise so that you can get the perfect amount of water where the volume is reading exactly 50.0 milliliters. And then record the mass of the water in your data table. For part 3, we're going to measure the mass of a packet of sugar or sucrose. The packet of sugar is given to you in your materials from Miramar College. You're going to weigh the packet of sugar, which includes both the packet and the sugar inside. And this is going to be your gross mass. Then you're going to empty the sugar into the waste bottle and weigh just the packet, right? The empty bag. Then you're going to take the gross mass of the sugar and the bag, subtract the mass of the empty bag to get the mass of the sugar in the bag. And you're going to make sure to record that in your data table. So this is what it looks like, right, for part J in the experiment. So again, it gives you a photo of an iron cube on a digital scale. Remember to record all of the numbers that you see on the digital scale. So over here, you should write 53.22 grams of iron. You're going to again record all of the numbers on the digital scale for your 50.0 milliliters of water. But again, we're recording that, the mass of that, and also the mass of the sugar that was inside of the packet. So all of these masses will be used to do further calculations in the post lab. All right, let's talk about the post lab. So the first part of the post lab asks you to find the number of moles and atoms in the iron cube. So again, it wants you to just copy the mass of the iron cube from part J1 over into your post lab. So again, that was the 53.22 grams of iron. Right, write the atomic weight or the of iron. So you can find that from the periodic table. And again, that's the mass of, it should really say molar weight, right, or molar mass, because even though it's the same number, you can see that the units over here are grams per mole, right? So it's we're going to be using these units, right? And we're going to use this as a conversion factor in the next section. But still, we find the number from the periodic table. Then we're going to calculate the number of moles of iron in the cube and the number of atoms of iron in the cube. So I did this part for you just so that you can see how to do it, and it's the same in the next two sections of the post lab. So again, we have the mass. We look up the molar mass, right, from the periodic table for iron in this case. And then we take the mass and the molar mass, right, and find the number of moles of iron. Remember that your units of grams should cancel, right? So grams needs to be in the denominator in order to cancel with the original grams of iron that you started with. And you'll be left with your units in moles of iron. Because we started with 4 significant figures, we want to report our answer in moles to 4 significant figures. I included 5 here and put a line after the last significant digit. And then I rounded to report the moles of iron in J1C. I'm including extra significant figures, right? Because as I continue to calculate, I don't want to round early, right? I want to only round at the end. So when I'm calculating the number of iron atoms in the cube, I want to start with the most number of significant figures that I can, right? So that when I multiply, there's less error. So we start with the moles of iron. We're going to use Avogadro's number as a conversion factor. So again, this Avogadro's number tells us how many, and I'm sorry, this is a mistake. It should not say molecules because of course it's just iron, right? So it should say atoms of iron. So 6.022 times 10 to the 23 atoms of iron and 1 mole of iron. And this gives us the number of atoms of iron in our iron cube. For part 2, we're going to do similar calculations, starting with the mass of the 50.0 milliliters of water that you measured earlier. We're going to find the molar mass of water. Again, you just add the mass of oxygen and 2 hydrogen atoms to find the molar mass of water. We can use the molar mass as a conversion factor to convert between the grams of water to the moles of water, just like I showed you in the previous section. And then once you have the moles of water, you'll be able to calculate the number of water molecules using Avogadro's number. And then once you have the number of water molecules, you can convert to the number of oxygen atoms and the number of hydrogen atoms, respectively. Remember that water is H2O, right? So there is 1 oxygen atom in 1 water molecule, but 2 hydrogen atoms in 1 water molecule. And the last section is the number of moles of sucrose in the packet of sugar. So again, we're going to want to copy over from the data table the mass of sucrose. We're going to want to find the molar mass of sucrose. The formula is given here, so you can calculate it, or you can just Google the molar mass of sucrose. Then you can, from the mass of sucrose and using the molar mass as a conversion factor, you can calculate the number of moles of sucrose, use Avogadro's number to calculate the number of sucrose molecules, right? And then convert that to the number of carbon atoms, hydrogen atoms, and oxygen atoms, right? Given the formula up here, you know how many carbon atoms are in 1 sucrose molecule. Same for hydrogen atoms and oxygen atoms. And then just note that the very last page is the summary of results, and that is actually part of the post lab.